in white essentially when they're new or edited.
And then they cool off.
And then they cool off to the color that that assigns or that describes their file type. And also the people themselves seem to flash up a little bit when they're active. You can see that here this guy is actually like periodically increased. So what does this down here? What does that tell us?
Activity during that time.
Yeah. So this is the frequency over time. Like here, we essentially have this dynamic histogram that floats out. So, can you like read the data precisely here? No. No. So, what do you think is the purpose of this type of visualization?
Mostly trend analysis.
Trend analysis. Any other ideas?
How the processes are different between the three.
Yes, so that you can see structure. I can see which type of project this is. But I guess it's also a little bit about entertainment, right? It's simply fun to watch, and it's great for a community to see how their project evolved. So this tool is actually like you can plug in your SVN repository and it will create those videos for you.
It's a code selfie.
Yes, it's a code selfie. I like that. So this was really popular back in 2010, 2011. Why do you think that is?
That's cool.
Yeah, so a lot of open source projects simply had a way to show what they're doing, and everybody could simply do it and create it. So this is also called organic visualization. So this is not so much about like there's like a subfield, a tiny subfield that is about more like giving people a feel or an idea of something without being too precise. Of course, you could do this better with bar charts. If you just want to be about precise data communication, but it's not the same. Like you engage people, you have some like organic feel to it.
Well, I thought it was interesting, like GitHub, if you click on graphs, has like stuff that shows a lot of the same data, but it takes like 4 graphs to probably not show quite as much.
Yes, and so actually the GitHub visualizations are not very good, especially the network visualization of like the dependencies between branches and forks and so on. So yeah. Any personal opinions about this piece that you want to share? Do you like it?
I think it's cool, but I don't see where I'd use it for anything.
Yeah. Okay, good. So this was something completely different to the other ones we had so far. That's also why I picked it, and I kind of like the music. Good. So, quick reminder about the no device policy. It's not been too much of an issue here, but just wanted to repeat this. And this is like the reason for that, because if you have like a Facebook notification blinking in the corner of your screen in red, your attention will be on Facebook and not on me. So like I probably won't win this fight, and therefore please don't use any devices in class when we don't use them for class activity. So let's talk about the visualization alphabet, marks and channels. So if you think about it, how can I visually represent two numbers, 4 and 8? You can give suggestions. How can I represent two numbers? Size, okay. What shape?
Square.
We have here square, 2. Okay, that's a different mathematical representation, but not a visual representation.
Velocity?
Velocity, yes, I'm not going to draw that. We could also do angle, or that would be essentially the pie chart way of doing things.
Well, wouldn't angle be like hue though? And you said hue wouldn't work as well, or?
No, you can actually you can clearly say this is steeper than this, and you can actually judge how much, but you can't say red is bigger than green.
These times from a single point?
Yes, that's position essentially. So you could think of more bizarre things like curvature and so on. So anything like that is possible. So this is kind of the alphabet that we're working with. So and I'll later show you a large list of how we can represent two numbers. So what we do here is we actually vary, like we have one thing, the marks that represent an item, and the other thing is a channel that essentially tells us, quantifies it somehow, that changes the appearance based on an attribute. So in case of position, the X here is the mark, and the position is the channel. And the channel is also called a visual variable. So if you have ever heard of Jacques Bertin, he kind of coined these terms of visual variables, and nowadays people call them marks and channels, but I also call them visual variables and marks. So the channels, so if I say visual variable, I also mean channel. I'm using those interchangeably. So which marks could we have? We could have the points, lines, or areas. And in 3D we could have a volume, but that's rarely used. We can use, we have a special type of marks for links, which are containment, connections, containments and connections. So like these are the basic, like if we have data items, these are the basic things that we can, how we can represent them. And if we have links, which is also an attribute type, then we could simply also use containment and connection here. Containment can of course be nested, so here is a Euler diagram of friendships, and so we can use this on multiple levels. And the channels are what controls the appearance. So essentially what we did here is we came up with a lot of different channels. They are typically proportional to or based on attributes. And proportionality is of course important for quantitative values, or based on attributes is things like color when we have qualitative attributes. So the key ones, and we've come up with more here, but the most important ones are position, shape, size, color, maybe tilt, and maybe volume. So, but essentially those four here are the key visual variables, or the key channels. As I mentioned, this was kind of formalized by Jacques Bertin, and he wrote this super influential book, Semiology of Graphics, in 1967, originally in French, but now you can actually get it in English too. It's still in print, and it's kind of the Bible for visualization researchers, because if you look at it, if you read it, you kind of discover, you are really amazed how much of the things were rediscovered later, and which he kind of forethought a while ago. And he really laid the groundwork, the theoretical principle for visual encoding. And this is the figure that he actually used. So he had position, size, gray value, texture, color, orientation, and shape. And for the different marks, he had points, lines, and areas. And you can see that he varied this a lot, and you can also see that he thought in terms of cartography a bit, but not only. And so texture, for example, is something that we don't really use a lot in visualization because it's not easy to distinguish, but we can. So when we want to use the marking channels, we can, based on how we change them, we can actually encode different data with them. So in this case, we have the mark is a line on the far left from your side. We have the mark is a line, and the channel is the length or position. And then we have one quantitative attribute, which is essentially encoded by the length here, and then one categorical attribute. So this would be A, B, or C. This would be the categories. So here, like this is what a bar chart can do. Like a mixture between categorical attributes and quantitative attributes. In a scatterplot, we would have the mark being a point, and then we have the channel being position. And here we could show two quantitative attributes. And this is great for showing relationships between those two quantitative attributes. If we want to add an additional categorical variable, we could add hue to that. So now we clearly see those two are in one class and this one is in one class, so we have a categorical variable added to that. And if we want another quantitative attribute, we could start varying the size. So like you could say, okay, I have a vocabulary of, like we came up with 15 different visual encodings. I could simply show 15 variables for every single point. Well, it's not like that. There is a limitation. So there is a certain kind of interaction between things. So like if, for example, you have a lot of points, then you would get clutter if some of them are really big and so on. You can also use redundant encoding. So here we're using length, position, and value. So length, obviously the length of the bars. Value, obviously how bright or dark this is. But we also use position. So like align bar charts use the size of objects, but they also use the position of the upper edge of bar charts. So like this is also why align bar charts are so efficient, because they actually use position and length. And position itself is the strongest visual variables, and length is the second most strongest. Here is an example from some weather channel. That was the snowfall in Boston in last year. And I just like, one rule of thumb is, if you create a bar chart, make it represent the data. Because here we have a bar chart, a bar that represents 5 inches of snow, which is about half the size of the 71 inches. And this is actually bizarre, because usually news agencies try to like overemphasize effects, but in this case they kind of underemphasized it totally. So it would be much more intriguing chart if you really showed this like little tiny 5 here, the 71 up here. So yeah, obviously don't do things like that, but people still show them, and this is really just like 2 numbers would be more efficient than that. So the rule here is use your channel proportional to the data, not a very surprising rule. So you can classify the channels into 2 types. You can say the magnitude channels and the identity channels. And you can see that they clearly map to these different types of data. So you can ask magnitude channels, you can ask how much, and their position, length, and saturation. And the identity channels is what and where, the shape, color, the hue of color, and the spatial region. Of course, you can use spatial region also for ordinal or quantitative data, but you can also use it for categories. So this is the classification that is in the book, in your in the visualization design and analysis. And so you have position on a common scale, position on an unaligned scale. You have length, like it's essentially 1D size, tilt, angle, area or 2D size, the depth, like a 3D position, color luminance, color saturation, curvature, and the volume. And this here is ordered by effectiveness. And people have done studies on how effective those various attributes are, and like this is really, it's not, every position here is not clearly super well understood, but we clearly know for like these ones here that this is the correct ordering. And then for the identity channels, we have spatial region, which is the strongest one. Then we have color hue, then we have motion and shapes. And these attributes or these channels also have other properties. So in this case here, which visual variables, which channels are used?
Position, color.
Position and color, yes?
And size.
And size. Exactly. So we have color that shows us something, and we have a redundant encoding with position. And we have the size of the bubbles. In this example that you already know, which visual variables are used?
Color. Color.
Yeah, only color in this case. So So there's a couple of characteristics how you can classify these channels. So we call a channel or a selective if its mark is distinct, or if a mark is distinct from other marks. So can we make out the difference between two marks? So for example, for categories or for shapes, we can clearly distinguish those two of them. And we can also clearly distinguish the position of these 3 points from these 3 points. Associative, does it support grouping? So in this case we can clearly see that position is great for grouping, but here we can't really, like with shapes, it's really more difficult to do grouping. And then we can have we have this notion of magnitude versus identity channels. Is it quantitative? Can we quantify the difference between two marks? And so we can think of, like, you can analyze these channels based on these ones. So can we see an order? Magnitude versus identity again. Can we see a change in order? And length is how many unique marks can we make and how many unique marks can we distinguish. So we, for example, know that we can distinguish only 10, 12 colors offline, like seeing, like not at the same time next to each other, but if you like have two colors, if you want to compare two colors, then you will kind of limit it to 10 or 12 colors in your visualization. But if you, for example, use symbols, you have a much stronger variety of marks that you could use. So position, as I already mentioned, is the strongest visual variable since it's really suitable for all data types. But it also has some problems. So sometimes it's not available. So if you have flow data, for example, if you have spatial data, then you can't use position. And this is also what I mentioned, that this kind of divides scientific visualization from infovis. And it can also lead to cluttering. So if you have like a lot of items, a lot of marks in the same spot, then position isn't that great. And it is actually, all of these attributes are yes for position, and we have a pretty rich vocabulary, so we can distinguish a lot of positions. So here we have, like, the scatterplot is the classical example for position. However, we're not so good at seeing position in 3 dimensions. So here we have, like, sure, there are some clues. We can, of course, in print or in projection, we don't have the stereo effect, but so we need to rely on other effects of depth. So, for example, like the size and the shading and so on, and occlusions. But it's not easy for us to read, like, for example, the exact value of this point. It would be pretty easy to read if we have a 2-dimensional scatter plot, but a 3-dimensional doesn't really work that well. So we can't really use position in 3D, yes?
So, getting highly theoretical, is it because it's on a 2D space, and perhaps if we had some hologram with 3-dimensional?
No, so people have, yes, it's better if you have stereo, like in a physical space, but we still have these issues of, like, we can't simply align them to a scale easily. We can perceive them better if we have it in a hologram, or in like, there's things like a cave or virtual environments and so on, or if you have a virtual glasses and so on. But you still have problems, for example, of occlusion. So, like, it depends always on your viewpoint, because if you, like, of course, if you look at it so that it's 2-dimensional, you can clearly see where it belongs to. But if as soon as you tilt and want to start the 3rd dimension, you kind of see that there's occlusion down here and so on. So I'll give many more lectures of why 3D isn't really such a good idea unless you have a very good reason of doing 3D. Okay, so this is the end of today. I'll have only a couple of slides left, so we'll actually get some time to spend on the next lecture next Thursday, and see you guys then.
Do any of the TAs have time to shoot a blog or